Hi, welcome to this lesson on calculus, the second derivative. Let's have a look at question 6. We're given a rough sketch below of the function g prime, so the first derivative of g, and we want to determine any stationary points, the intervals of the function g, where it increases or decreases, and then classify any intervals of concavity and if there's an inflection point. Okay, so let's again recall from the interpretation of this graph, we're looking at the derivative already, g prime of x. And this derivative is a cubic, not a cubic, a quadratic function, okay, a parabola. All right, so first of all, I'm given two x-intercepts here, -2 and 0, and -8 and 0, and a turning point with a y value of 9. We don't know the x value, but we can work it out by using the property that the turning point is symmetrical about your parabola. So halfway between -8 and -2, so -8 plus -2, so that's -8 minus 2, over 2, so that's -10 over 2, which is -5. So at x equals -5, that's 3 units away from each x-intercept. So this point here, P, is -5, 9. So we can write it in vertex form. Well, not f, rather, this is g prime. So g prime of x, that's equal to a times x minus p all squared plus q. But we know p and q already, so it's a times x plus 5, because if I put -5 here, it becomes 0, and then plus 9. And also, based on the shape of this quadratic, right, sad face with a max turning points, the a value's got to be negative. Okay, so how do we find that a value? Well, let's substitute one of the points. So g prime at -2 must equal 0. Well, then that means that a times -2 plus 5 is +3, and 3 squared is 9, plus 9, that must equal 0. So I have 9a equals -9 by taking the 9 across, and then a equals -1, which is what we expected, a negative value for a. So therefore, g prime of x is -1 times x plus 5 all squared plus 9. Okay, and we can expand that out, so it's negative. Don't forget the negative outside here, so that's x squared, double the product is 10x, 5 squared is 25, and then plus 9, but then we need to distribute the negative out, so -x squared minus 10x, you're going to have -25 plus 9, so that's going to give you -16. Let's double check that, -25 plus 9, great. Okay, so that is g prime of x, that's the first derivative. Okay, and knowing the first derivative, we can write down some of the properties. So stationary points of the original function g, that's when your g prime x is equal to 0. But that's equivalent to saying, when is this graph equal to 0? Well, that's at the x-intercepts, -8 and -2. So x equals -2 or x equals -8. So these will be the stationary points of the original function g, which was most likely going to be a cubic because the derivative here is quadratic. It's a degree lower. Okay, what about intervals of increasing and decreasing? So increasing is when your first derivative is greater than 0. So visually, we're looking for when is this graph positive. So it's positive up here. So therefore, the intervals x is an element from -8, open brackets, to -2. Okay, what about intervals of decreasing? So visually, what does that mean on the graph? That means your first derivative is negative. So where all the values, the y values of this g prime graph are negative. So that is to the left of -8. So x is an element from -infinity to -8. Then it takes a break and becomes positive up here. And then from -2 again, -2 to positive infinity, the graph is negative. So the g prime is negative. Therefore, the original graph is decreasing on that interval, -2 to infinity. All right, so that is the stationary points and the intervals of increasing and decreasing. What about concavity and inflection points? Well, for concave down, mathematically, that is the second derivative less than 0. So I know my first derivative is this function here. So my second derivative, so say g prime of x rather, okay, that's going to be -2x minus 10 using the derivative laws on the first derivative function. Okay, so that implies -2x minus 10 less than 0. So let's solve this algebraically. Okay, so I'll bring the 2x across. So I have -10 is less than +2x. So the other way to read that is 2x is greater than negative 10. So I get x is greater than negative 5 when I divide both sides by 2. So interval, x is an element from negative 5 to infinity. That is your graph concave down. So it's got that shape and it is lying below your tangent lines. What about concave up? So at concave up, let's go up here, concave up. So that's when the second derivative is greater than 0. So again, algebraically, that's negative 2x minus 10 greater than 0. Then I take 2x across, so I have negative 10 greater than 2x. The other way of reading that is 2x is less than negative 10. And then dividing both sides by positive 2, I get x is less than negative 5. So interval notation, that's from negative infinity up to negative 5. There your graph will be concave up. It'll have that shape. It lies above its tangent lines. So let's go to our graph here. Can you see that the turning point here of the first derivative, okay, is actually your inflection point? Because if I solve g double prime equals to 0, that implies negative 2x minus 10 equals 0, which is 2x equals negative 10. Therefore, x is negative 5. So it turns out that because it changes, so from the left, it's concave up, okay, to the left of negative 5. And then to the right of negative 5 over here, it changes to concave down. Okay, so therefore, because it changes concavity at the point negative 5, we can say that negative 5 is the point of inflection. And how nice that the visual representation of points of inflection using the first derivative function happens to be the stationary point or turning point of that derivative function. Okay, and that's kind of expected because we're solving g double prime x equals to 0. So if it's the derivative of the derivative, so there's that gradient line is the derivative of that derivative. Okay, and it's 0 there. So it all makes nice mathematical sense when we can connect all the concepts together. All right, so that's having a look at the second derivative. I'll see you in the next one.